Hi, my name's FLETCHER. I'm an engineer on the delivery engineering team here at Netflix. I've been working on Spinnaker for around about 3 years now, a little over. So I'm here today to do a little bit of a semi-deep dive on Orca, which is the central orchestration component of Spinnaker. It's the thing that coordinates all of the different stages you configure in a Spinnaker pipeline, or runs tasks that you run from the UI or from via the API. It doesn't really do any of the work itself, but it ties everything together. It's the workflow engine at the core of a Spinnaker pipeline. And recently we rolled out a pretty major rewrite of the core of that service. So I want to take you through some of the history of where we started with Orca, why we decided we needed to do a re-implementation, and where we are now and where we can go from here. Just in case anyone's not super familiar with how some of the internal stuff in Orca works, I'm going to run through some of the basics of just how a pipeline operates, what stages are, what tasks are, that kind of thing, so that when I'm talking later on, it will be clear what I'm talking about, hopefully. So if we look at a typical simple pipeline, the kind of thing you configure in Orca yourself, you've got a pipeline that consists of several stages that you configure. Each of these are what we call top level stages. So those are the ones that you see in your configuration view. So in this example, we have a bake stage, a manual judgment, which is just a, is this okay to proceed, and a deploy stage. Pretty straightforward. Each of those stages can decompose internally into Orca into other stages, so their behavior can be implemented partially by other stages. So this gives us kind of reusable blocks of behavior, and we call these synthetic stages. So what these are is a stage that is added programmatically into the pipeline by one of the top level stages in order to get some of its work done in using a reusable block. And some of those synthetic stages are kind of shared between multiple different top level stages. So in this example, we've got a deploy stage that decomposes into two individual deploy stages that are targeted at a particular region in AWS, which is exactly how a real deployment stage works. We'll run a deploy for each region in parallel as an individual synthetic stage. A synthetic stage itself, or any stage, maybe uses tasks. So in this case, we have a create server group task, which will just fire the request to AWS. Then we have a monitor deploy task, which will monitor AWS, polling it to see that it's accepted that command and that the work is in progress. And then we have another task that's wait for up instances. So that's waiting for the instances in the new server group that's been created to actually be up and healthy in discovery, reporting success via their health checks, that kind of thing. This is a slightly simplified view of what a real deploy does in terms of its tasks, but it's pretty accurate. And the last thing there, the disable old server group, is another synthetic stage. So synthetic stages themselves can have synthetic stages. And we use these typically in the deploy stages to implement deployment strategies. So if you've seen like Red, Black, or Highlander strategy, or the custom strategies that you can implement yourselves, then that's how we do that. It kind of tacks on some extra stages at the end of the deploy. So in this case, we're doing a straightforward thing that's just going to disable the old server group, and that itself is obviously implemented by some tasks. So the key thing here is that stages are kind of groups of tasks that can be then further grouped into larger stages. And tasks are the atomic individual operations. They're very, very simple. They do one thing. They can be repeated. So a very typical pattern we have is something that goes and makes a request, being one task, then the following task being something that goes and polls to see if that work is then done. So that task will get run over and over and over until it's successful. And there's kind of a little delay in between each run. But some of those can be extremely long running. So we have canary stages here in Netflix that run for days. And there's literally a task spinning there saying, is this canary finished yet? Is this canary finished yet? Give me the latest score, that kind of thing. And we'll talk about how we could maybe make some of that process better, given the new capabilities of Orca shortly. So let's dive into the history. Orca v1 was released, or was initially put into operation coming on for 3 years ago now. It was kind of the one of the first components written of Spinnaker before it was open source. And that was kind of my task when I first joined Netflix. And yeah, we initially had some decisions to make about how to implement this thing. We knew we wanted a workflow. We knew we did not want to be tied specifically to AWS, because one of the founding principles of Spinnaker was that we did not want to be running on any AWS specific services, because we always envisioned this world where Spinnaker was open sourced and could be used to run on multiple clouds. I think this even predated Google's involvement, but we had been bitten writing Asgard before, where the preceding system that Spinnaker replaced. And what happened there was that we'd get nice people doing awesome work in the open source community, but on forks that were designed specifically for like Google Cloud, or I don't know exactly what forks were there, and we would then not benefit from that innovation because it couldn't be folded back into the core of Asgard very easily. So with Spinnaker, we really didn't want to have anything tied specifically to AWS. We wanted the cloud providers to be modular. So we want to use Simple Workflow, which is the Amazon offering for doing this kind of thing. In the end, the decision was made to experiment with using Spring Batch. It just seemed, at the time, seemed simple enough. We all knew Spring pretty well. We were using Spring for the bootstrapping the components of Spinnaker anyway. It gave us workflow concepts we need, such as branching, joining, conditional steps. It gave us exception handling. It gave us, this notion of a task that can poll something and return a still running status, and then can return a complete status when it's done. It gave us things like parameters that could be fed into a job and a context that follows along. And it gave us life cycle events that we could monitor. So, it didn't turn out to be the greatest decision, but at the time it seemed reasonable. And we also have to bear in mind that at the time I was working in a different time zone, 8 time zones away from here, and I was my communication with the team was not as perfect as it could have been. So, in retrospect, we may have made different choices, but the amazing thing is it held together for 2 years and got up to some ridiculous scale before we decided to actually, it was reaching the point where we wanted to swap it out. So, and a key thing is that there were a lot of things we didn't know at the time. We kind of envisioned what we wanted to do with pipelines, but my understanding, or I think our understanding generally as a team of what a pipeline is and what it needs to do has changed dramatically over the past 3 years. So it's easy to say with hindsight, this was a wrong technological choice, because what we find is there's kind of a mismatch in intent between Spinnaker and Spring Batch. Spring Batch is not designed for distributed systems, really. That's not entirely true, but it's not designed for distributed systems in the way we're trying to use it. It's not designed for having thousands of pipelines configured in a data store. It's designed for having a bunch of batch jobs configured in some static code or an XML. It's not designed for flexible executions that can change what they're doing at runtime and make decisions about exactly what their structure are going to be at runtime. It's not really designed for ad hoc work. It's the way Spinnaker, I'm going to get into this in a little bit more detail later, but restarting pipelines turned out to be really problematic with our Spring Batch implementation. And failure handling is not making sure that things like, if we lose an Orca instance in the middle of a deployment, what state is that server group that it was deploying in, and what state is the previous server group in? Those kind of things are pretty critical and were cumbersome to implement with Spring Batch. And this is not to say Spring Batch is a terrible framework at all. It's just we were using it for something it's not really designed for, because it had some of these runtime features or these kind of topological features that we wanted to use in terms of what a pipeline is. But really, it's not the tool that's fit for the purpose we were trying to use it. It's very good at what it does. We were trying to extend it way beyond its capabilities, I think. And one of the things we found is that, awesome, I think the battery's gone flat on my clicker. Sorry, I'll use the keyboard. Good. One of the things we found is there's a different granularity of concepts between Spring Batch and Spinnaker. So Spinnaker decomposes things as a pipeline, a stage, and a task. pipelines have many stages, stages have many other stages, or many tasks, or both. Spring Batch has just 2 levels. It has a job and a step. So a job is just a big long chain of steps. It's very procedural, it's very straightforward, but it doesn't really have that hierarchy of composable elements that we wanted from Spinnaker. And one of the things that this made it really difficult to do was to trigger events when a stage started or completed. Because as far as Spring Batch is concerned, this is just another step running. It doesn't know anything about the notion of stages. So it turned out like the amount of code we had to write to get that working was just ridiculous. And this is something we bumped into again and again. It's just, it was trying to bash a square peg into a round hole. You know, the amount of code we'd have to write to get Spring Batch to do the thing we wanted it to do turned out to be excessive and more complicated than just really doing it ourselves. So yeah, there's kind of a missing concept there of the stage. And above all, you know, Netflix doesn't really do stateful services. The way we typically operate software in the cloud is things are resilient to failure. Things are scaled as needed in order to support the traffic they're receiving. Things are not storing state and sensitive to being destroyed, because, you know, everyone in this room has probably heard of Chaos Monkey, the service that just will knock instances out of the cloud at random. Did not work with Orca in its initial state because failure of an instance was catastrophic. We would lose all the work running on that instance, because one of the really annoying things that Spring Batch does is it actually pins a thread for the entire run of a job. It just locks a thread because, you know, Spring Batch is intended to be fairly short running. It can take, you know, it's envisioned to take minutes, maybe hours even, but it's only not days. And it's envisioned to be busy all of that time, which Orca certainly isn't, because a lot of the time it's sitting waiting for some other service to do something. It's waiting for Amazon to deploy something into the cloud. It's waiting for Amazon to enable some instances. It's waiting for a Jenkins job to complete. It's waiting for another pipeline to run. It's waiting for a user input. All these kind of things. So it's, you know, it turns out that Orca is actually idle for a hell of a lot of the time. And having it spinning, locking a thread throughout that time is just nuts. One of the things we found was that we couldn't even red-black Orca. So we couldn't, you know, a typical deployment at Netflix is to create a new server group, enable all the instances in it. As soon as they're healthy, disable the old server group and leave it around for a certain amount of time in order that we can roll back very easily. And that was impossible in Orca because we had to drain work off it. So we ended up with this elaborate system where we could have a bunch of old server groups running for days and days after we'd rolled new ones out with updates. And we tend to move pretty fast, so it's not unusual for us to push 2 or even 3 versions of Orca in a day sometimes into production. So we would end up like 5 or 6 old server groups draining work down for days of long-running canaries, and you go and look at what's running on there. It's like one job, one guy's canary that's been running for 72 hours. And we, you know, this is just not where we want it to be. And it's really difficult to apply hotfixes to in-flight execution. So, you know, if somebody says, oh, my pipeline's behaving in a weird way, and we go and analyze what the problem is, and it actually turns out to be super simple, we can't ship that fix into production and have it pick up under that running execution. It's impossible. You know, they'll have to wait for that one to complete or cancel it and start it again on the new hardware. So ultimately, this is not where we want it to be at all. You know, we want it to be in a world where we're a more typical, well-behaved Netflix service where we're resilient to instance loss. We're able to restart pipelines, because that turned out to be an enormous problem. The way, I'm going to get into some of the planning of pipelines later, but the way Spring Batch requires everything to be statically defined up front, so you have to know exactly every single step the job is going to take up front. Turns out to be really difficult when you're then mapping a pipeline onto that, and the pipeline may be reactive to differences in the topology of the cloud that you're deploying to. So, you know, you try and restart something 4 hours later, there's another server group in place. There are more instances, there are fewer instances. Things look different. Somebody's changed the load balances in the meantime. You can't just rerun all those same steps and assume everything's going to work, because the world has changed. And a key thing is we wanted to distribute work across the cluster. We don't want one pipeline pinned to a single instance of Orca for its duration, especially some of these really long-running ones. It's bad enough for a deploy that takes 10 minutes. It's terrible for a canary that takes 72 hours to be pinned on a single instance. And if that instance fails, it's gone. That's not what we wanted to be doing at all. So the first step in this that took quite a long time was moving from Orca from V1 to V2. So if any of you have dug into the JSON of a pipeline execution, you may have seen like a execution engine flag. So V2 was another problem we had was that Spring Batch concept had kind of leaked out of the abstraction of pipelines. So particularly around if anyone had written a custom stage, the components we used to define stages had some Spring Batch types in their API, which is bad, but we didn't, at first we didn't have a great abstraction, and then we just never found the time to build a good abstraction until V2. So the purpose of V2 was to not change any behavior. Everything still runs in Spring Batch. Everything runs in the same way. Pipelines are composed in the same way, but all of the Spring Batch code is isolated and put into a single module in Orca. And then in theory, we can swap that module out for a totally different execution engine. So this turned out to be, it's a transactional step. It's kind of a thankless task, and it took a heck of a long time. And it was, inevitably there were things that didn't work quite as perfectly as they did. So we wanted to get away from that as quickly as possible. But it was a necessary step. We had to untangle the tentacles of Spring Batch from out of our system. And earlier this year, we started work on Orca v3. So Orca v3 was to do that final step of replacing the Spring Batch module with something else. And we ummed and ahed for like 2 years about what we wanted to move to. I've been keen to rewrite Orca since almost day one of it being out there running pipelines, when some of those limitations really started to become apparent. And, we looked at Orca for quite a while. Orca's really interesting, but it turned out to be kind of difficult to integrate its clustering with Netflix's service discovery. It's not impossible, it's just a little cumbersome and a little difficult to unit test and difficult to kind of have any confidence it's working when you push it to production, the way we were trying to do it. Orca is also, it's kind of difficult to trace execution through Orca actors that can be running on. If you get a stack trace from one of them, it's not terribly useful because messages are sent across a message bus. So the stack trace is kind of localized to where that message has been received. And also, we're not really clever enough to write Scala in our team, so we didn't do that. So we came up with what became increasingly apparent is we were kind of looking around for a new framework to use. Let's use some new framework to implement this workflow system. But none of them were really great fit. And what we wanted really was something that was simpler and more flexible than any of these things offered. And we decided we're just going to roll our own because we know what we need to do. We're not going to end up building a square peg or a round hole because we know exactly what we want. And it's actually not as complicated as it may have looked a couple of years ago, now that we understand the problem a whole lot better than we did. So we came up with a simple message queue system, and we decided initially we wanted to have it running on Dynamite, which is a Netflix version of Netflix-specific wrapper around Redis. I guess you could describe it as, that allows for cross-region replication. And Rob, jump in if I'm talking nonsense about what Dynamite is there, but I think that's a pretty fair description. In the end, we haven't got there yet. I'll talk about that shortly. We're running it on Redis, just plain Redis, which is what Orca was using for its persistence generally, although the persistence of this message queue and the persistence of Orca's pipelines are completely separate. They could be running on separate Redis instances. They could be running on completely different stores. We also have an SQS implementation we used as a proof of concept to make sure that we weren't making the same mistake we used before by getting Redis concepts tangled up with the actual implementation of, or the abstraction we were building around this message queue. So we don't use that ourselves, but it's available in the open source repository if anyone's on AWS and would rather use SQS than Redis, it's there. Although, given that we don't use it ourselves, how perfect it is, I'm not sure. But it's, you know, fundamentally it does the right thing. So the key thing we wanted to do with this messaging system is have lightweight messages that are very, very simple, carry minimal state, processed in like maximum of a few seconds, and that's like the time it would take to make a request to Cloud Driver and get a response. That's kind of the longest running work they should do. Those messages should represent like either atomic state changes on the pipeline or an action to be executed, preferably not both. We want messages that can specify delivery time so that when we're doing things like waiting for a configured amount of time, we can just push a message that will only get delivered way in the future at the point when that wait's done. Or if we're waiting for a canary to complete, we can push a message way in the future and not like keep having to poll it all the time. We haven't quite got to that yet, but we will pretty soon, I think. And we also wanted work that would just naturally kind of flow across the Orca cluster. So any instance that's active in the Orca server group can read a message at any time, doesn't matter what pipeline it's in reference to. When we read Black Orca, we want just the work to just roll over onto that new server group instantly and not have to drain work off of old instances that are disabled. So this is what we built using Redis for the store. So what we have is a queue that is polled constantly by each instance in the Orca cluster, each active instance. So when we take an Orca instance out of service discovery, when we disable a server group, for example, it stops polling at that point. So it's only polling while it's active. So as soon as we disable things, they drain work for like a couple of seconds max, and then they just become idle almost instantly. So our message types boil down to, as I said, it's kind of state changes, simple atomic state changes, or it's very simple actions. So start and complete execution, start and complete stage. So these are the things that all they're doing is like set the status to running, set a start time, figure out what to do next, push a message onto the queue that says go do this next. So in the case of start execution, it would be set the pipeline status to running, set the start time, figure out what is the first stage or stages you're going to be running, and fire start stage messages for all of those. And that's exactly the same all the way down all of this entire hierarchy of messages. The two that are kind of slightly more complex are the start stage, because when that gets handled is when the stage works out, okay, what tasks do I have to do? Do I have any synthetic stages that I need to run first or afterwards? Are there any things, other stages I need to run in parallel, such as if I'm doing a deploy, have I got multiple regions to deploy, and I need to create a stage for each of those? So that's the kind of most complex bit of work, and then obviously running a task, which is the point at which it actually takes that task definition, that class that's been written to perform a particular action, loads that up and throws some context at it and has it do its work. So if we get into, let's have a look at how this differs from how in operation, in construction of a pipeline and in operation from how it was running on Spring Batch. So first of all, we'll take a look at a pipeline in Spring Batch and how it gets built and run. So we've got a simple example here, a bake, manual judgment, deploy. Those are the top level stages that are configured. When the request comes into Orca, this is what it knows about that pipeline, is that it consists of these three stages. So under Spring Batch, the first thing we would do is go and look at that bake stage and build the synthetic stages and the tasks. So the little circles here represent tasks, and the grayer stages, which I hope the contrast on the screen is okay for, are the synthetic stages. So the bake is decomposed into two bakes, one for each region, each of which consists of a number of tasks. So we would go build all those things out. We'd figure out that judgment is just a single task. We'd then go and build a bunch of stages for deploying, and then the strategies that go behind that, and all the tasks involved. So at that point, we'd have this complete execution plan. And then we would start running it, and it goes through all of these stages and all of these tasks in order. and runs them. And this is where we get into that notion of it being a little bit rigid under Spring Batch. It's not flexible. If, for example, let's imagine that manual judgment doesn't get done. Nobody approves it because it's a weekend. And in the meantime, somebody's been tinkering around on the weekend and rolled a couple of server groups over and changed load balancer configuration. By the time that deploy stage runs, the world looks different to how it did at the point we were planning the execution. And that can totally invalidate the assumptions that were made when planning the pipeline. So it's super inflexible. It's also really bad for restarting, because if we, let's say, the deploy stage fails, one of the deploy stages failed, but it fails for some transitory reason and somebody wants to restart it, we let people do this. We let people restart a particular stage. The problem is with Spring Batch, it doesn't have any notion of, or the implementation we built on top of it didn't really have any notion of, okay, pick up work from here and carry on. So we would come in with knowledge of what the pipeline was trying to do before, all of these stages and things built out, and then we had to kind of reconstruct the Spring Batch job underneath it that was trying to do this. And it's a different thing because you already know all the synthetic stages and tasks, which you didn't when you first ran. So it's like almost a completely different code path. And it was just a horrible tangled mess of things that would fail quite a lot. When things restarted, it wouldn't behave exactly the way it did the first time round. It was pretty horrendous. So I was super keen to get off of that. And it was really frustrating to try and fix. People would come to us on call and say, oh, I tried to restart this pipeline and it's not really behaving the way I thought it would. And it was, as somebody who was familiar with the Orca code base, you know how horrible that code is and just don't want to get in there and fix it, because, like the only sane thing to do is burn it all down and rewrite it. So let's have a look at the differences with how it runs now on the messaging queue system. So we come in with the same exact notion of the top level stages that we did before. When we start running it, the first thing it does is, okay, let's start with the bake stage. I'm going to do this in parallel. I'm going to plan it, or plan those bake stages out, plan the synthetic stages, plan the tasks, and then I'm just going to run them. Don't care what's downstream yet. Doesn't matter. Because we can build that at runtime. Okay, that's all done. Let's do the judgment and run it. Great. Let's do the deploy. We'll figure out that we have these two parallel deploys and they have synthetic stages, but we don't care about what those synthetic stages are going to do. We'll just kind of create them, and we know at the point where we fire a start stage message for that particular stage, it will go and work out what it needs to do. And then it will run it straight away. So it's much more reactive. We don't have that problem of if somebody leaves the manual judgment sitting there for a weekend and the entire cloud changes, and the mitigation actions that need to be taken by the deployment strategy to say how many server groups does it have to disable. That could be a different number on one day from another day. The only sensible time to make that decision about how many server groups it needs to disable and which server groups they are, what their IDs are, is at the point you're just about to do it. Restarting becomes incredibly simple, because all we do is we delete all of the tasks and all of the synthetic stages downstream of the point you want to restart, and then just run it again. Just fire another start stage message and it goes off and does it again. Really, really simple. There's no locking of threads. There's no, all these messages are consumed across different instances in the cluster, which has really freed up a lot of things. Now we read Black Orca, we can do what we like. We're not worried about instance loss. We can actually restart things very, very simply. We can, even when we do have really catastrophic bugs, which we had a couple of times when in early stages of this implementation, we can actually recover the work pretty easily by just, you poke a couple of messages back into these Redis-based queues and things just start up again. There's no complicated trying to map pipelines onto Spring Batch and then get it back running in a particular state. Again, it's way, way simpler. We can do it on the terminal. It's so easy. So at the risk of going a little too deep divey here, I thought it might be interesting to have a look at how the queue itself actually operates. And you can see how simple it is. So the queue schema is composed of kind of three main buckets in Redis. We have the queue itself, which is a sorted set of message IDs with the score being like a timestamp of when it should get delivered. We have the message bucket itself, which is just a hash of the message ID to a JSON serialized representation of the message payload. And messages, as I said, carry virtually no state. They have like an execution ID. Some of them have stage IDs, some of them have task IDs, and some of them have status. So things like a complete task would have a like success, failure, still running kind of status on it. But that's all the state they have. They're not carrying around like huge payloads at all. Oh, they do have some attributes for doing runtime stuff like traffic shaping and other interesting things that I'll briefly mention at the end. The third bucket is another sorted set of message IDs with a score based on the time they should get retried. So the idea of this is the bucket representing messages we're currently processing. If we don't acknowledge them in a timely fashion, something else is polling that sorted set, that queue, and we'll put the message ID back on the main queue because that indicates an Orca instance fell over in the middle of processing this message and it never finished, it never acknowledged it. So let's have a look at what successful message handling looks like. So we have a push operation on the queue. So this can be coming from the edge of Orca where it receives an API request from the UI or from an API user, and it says, okay, go start this execution. Something will push that message onto the queue. Or it can be from handlers for other messages. So the start execution message gets handled, and the result of that is it pushes messages to say, start these stages. And the start stages handler pushes messages to say, go start this other synthetic stage, or go run this task. That's the push is kind of done by all of those different components. And what a push does is it puts the JSON of the message onto the messages queue, assigns it an ID, and puts that ID into the queue with a time at which you should deliver it, which is by default right now, but it doesn't have to be. It can be in any time in the future. It's just a timestamp. Then we have a poll operation. So this is reading off from the queue. This is happening at 10 millisecond intervals, I believe, on each Orca instance. So there's this process, one thread is dedicated to just reading this queue, and it takes a message and hands it off to a handler, which runs in a different thread from a thread pool. But there's this one thread dedicated on each active Orca instance that's just spinning and polling the queue all the time, single thread. And what that poll operation does is tries to read the message, and it just moves the ID from the queue to the processing queue. And it says, okay, if this doesn't get processed within, let's say, a minute, I think it is a minute, then we're going to try again. And that's how it decides what the score will be on that processing queue sorted set. So then the handler goes off on another thread and does whatever work it needs to be, planning a stage, changing some statuses, pushing more messages to the queue, that kind of thing. And then it will come in and acknowledge the message, hopefully. And that just deletes everything off the queue. Done. At that point, the messages are gone. You don't need them anymore. All this data is ephemeral. So what does failed message handling look like? I've kind of alluded to this with the acknowledge and retry stuff. The push is exactly the same. Message comes in, gets assigned an ID, put on the queue. The poll is the same. Something comes along and reads the message and moves that ID across to the processing queue. But 1 minute later, it hasn't responded. It hasn't acknowledged the message. So the other poller that is sitting polling on a slightly slower interval than 10 milliseconds, I think it's like every 30 seconds or something, it comes along and looks at this processing queue. It just because now the timestamp at which we should retry is now in the past. It just says, oh, okay, let's bump that ID back on the queue. Simple as that. Then you get a retry because some other Orca instance or the same instance is going to go read that ID off the queue again. It's super simple. This gave us like really simple and powerful resilience to instance loss. We can red black Orca, we can lose instances, we don't care. we can even set chaos and monkey loose on Orca, which is nice. But I guess the big question is, does this scale? Because what are we trying to do here is nicely summed up by this tweet that somebody found yesterday, and I put in my slides. There are only two hard problems in distributed systems. Number two, exactly once delivery. Number one, guaranteed order of messages, and number two, exactly once delivery. We're not really worrying about message ordering here so much, but we are trying to do exactly once delivery, which is, you know, a non-trivial problem. So how do we, you know, we have typically at Netflix right now, we're running 6 Orca instances at any given time in our cluster. We're probably a little over provisioned at that, to be honest, but that's kind of historical. We were using 6 under Spring Batch, and we've just never really taken the time to think, well, maybe don't need that many. So how do we prevent a message gets pushed on the queue? How do we prevent multiple instances reading that same message and processing it at the same time, given that these things are polling like every 10 milliseconds on that queue? So we have kind of concurrent read protection. So the process works approximately like this. Get the first message ID with a delivery time that's less than right now off the queue. Try and set a lock for that ID in an atomic fashion based on the instance. And if you're able to set that lock, read the message payload and move that message ID from the queue to the processing queue. In Redis, this looks like this kind of pseudocode. So we're using Redis's set NX operation to set, you know, it sets a value, and only if it's able to set that value, it returns true. So the point of convergence is the Redis store, and that guarantees that we can only set that lock once, and only if we're able to acquire that lock will we go ahead and read that message. Otherwise, the poll operation will not. So it's really interesting to look at how much this saves us. We actually have, there's an else in the real code, there's an else block there that sets an Atlas metric when this lock fails. And this is what the graph looks like. I pulled this from the data on Friday last week. And this is how many failed reads we're having in a typical minute. It's like across the cluster sorry, not failed reads, but like per second. I'm sorry, yeah, not per minute. So this is how many times an instance is trying to read a message off the queue but failing to set the lock because another instance has already read it at the same time. And you can see it's like 30 times a second. So this is saving us a hell of a lot of concurrency issues. And I'm not really aware of any times where this is not working for us. I mean, we have a single Redis, so we don't have a problem with that set NX operation being non-atomic. But it's, you know, it's a kind of, it seems to be kind of exactly once delivery. It seems to work pretty well. I think we would have heard about it by now if it wasn't. We also have a notion of kind of concurrent write protection, which is more for, this lets us be a little bit lazy about how the messages work. So we store a message fingerprint like a CRC of the message on push. And if another message that looks exactly the same gets pushed later, we just ignore it. Bear in mind that these messages get destroyed at the point when they're successfully read. So if we do ever need to push a message that does look exactly the same, we can do that. This means that we can do things like when we have parallel branches in a pipeline, at the point where the stage ends in any given branch, it can send a message saying complete execution. And then the complete execution message handler looks at that and goes, well, hang on, there's a bunch of other branches here that are not run, that are still running. So I'm not gonna do anything. And we don't care how many times different stages fire this complete execution message because we know ultimately only one will get processed by the handler at the point when all of those stages are finished. So this write protection is not really for concurrency problems so much as just letting us be a bit lazy about sending the same message a bunch of times and not having to worry about it too much. And we also have some metrics around that, and that saves us, you know, we have certain types of messages that we totally expect to be sending duplicates of. So we see the metrics coming through for that, and that's fine. So that's kind of how the queue works in a nutshell. And it's really straightforward, and it gives us all of those things we wanted around resilience to instance loss, letting work roll across from old server groups to new server groups, letting work be distributed across all the instances that are active. So where can we go from here? What's the future? Some of the way things work in Orca are still very much built with the assumptions that not the assumptions, but the restrictions that we had when we were running on Spring Batch. So, for example, a wait task really does poll every 15 seconds. It doesn't really need to do that anymore, and at some point we'll get to rewriting that. A manual judgment stage does the same thing. It polls every 15 seconds to see if somebody has clicked the button, and it doesn't need to do that because we could just stop execution at that point and then send another message when somebody does click the button just to restart. That'll come pretty soon. One of the things that's a bit horrible in Orca right now is stages can have a notion of actions that they take if they ever get cancelled. And cancellation can either be because somebody comes along and presses cancel on the pipeline, or it can be because another stage running in parallel failed. And that means you want to stop execution of everything in that pipeline, and you want to, clean up anything that it might have been doing. So Canary stages have cancellation routines. Deploy stages do, a couple of others. I forget exactly which ones, but and they were kind of in Spring Batch because of that inflexibility of the structure of the job. Those would just run right there in the current executing thread, and they didn't really mutate the pipeline at all. So it was kind of difficult to track exactly what they were doing. They couldn't be super complex. They couldn't be very clever. That restriction doesn't exist anymore. We could have cancellation routines that are adding new stages into the pipeline or adding new tasks into the existing stage and just running like regular stages using exactly the same message queuing semantics that anything else does. We have a rolling push deployment strategy. I don't know if anyone has ever used that, but what that does is it's kind of hot deploys a server group. So instead of creating a new server group and spinning up new instances and then disabling the old one, what it does is it changes the launch configuration of the existing server group to use a new AMI, and then it just one by one knocks out each of those instances in the server group and waits for them to restart, waits for them to get restarted by Amazon. Because we didn't know exactly how many instances were going to be there at runtime, and obviously we didn't want to make any assumptions about that. And also, this gets used by some pretty complex apps that can have like really aggressive auto-scaling policies switched on and can have really non-deterministic numbers of instances at any given time. Trying to plan that work, like let's create one destroy instance task for each of those instances, and then like half an hour later, we'll hope that it's actually got all of them, is not going to work. So the way the rolling push strategy worked before, it would create a single set of tasks for destroying one instance. At the end of that, it would figure out, okay, are there any more instances I haven't done yet? If so, go back around, like erase the context of these tasks and pretend we're running them again from scratch with a new instance ID. And this was just because we couldn't mutate the number of tasks that were in that stage, given the way we had to map the pipeline onto a Spring Batch job. Now we totally can do that. We can have that stage lay track in front of itself and just create new tasks as it goes, and that's something we'll address at some point. I mentioned Dynamite earlier, which is Netflix's kind of multi-region wrapper around Redis. So at some point we may want to have the queue migrate onto Dynamite. There is actually a library that's extremely similar in some of what it does to how we implemented the queue, called Dino queues. But it does seem to have some issues as far as I can tell with transactionality and concurrency, because one of the things you can't do in Dynamite is have transactional operations that depend on, in certain circumstances, I think there are some sort of multi-key transactional operations, yeah. So there are some restrictions there that would make it a little bit more difficult to make those guarantees around exactly once, hopefully exactly once delivery. But at some point we might investigate that. But given that these messages are so ephemeral, it may not be that big of a deal. We definitely want to move the storage of pipelines, the kind of execution that is in flight. We want to move that to a model where it's replicated across regions, so we can do evacuations of a region in Orca. But the messages on the queue themselves may not be as problematic there. We could probably just take a dump of the state of those tables in Redis and just recreate them on the new thing in a couple of lines of code. So it's less of a problem. But there are some really exciting and interesting possibilities. There's much less code involved now, and it's much less complicated, I think. I would say that I wrote it, but it's a lot less horrible to try and debug than it was with this stuff that was mapping stuff onto Spring Batch, and then we don't have all these integration tests that are just proving that we're using Spring Batch right. Yeah, it's a lot more pleasant to work with, and you know, the future looks pretty bright for the kind of things we can do. And with that, I think if anyone has any questions, if not, you can ping me in the Slack channel on that handle there, or I'm also on Twitter. But yeah, fire away.
Do you have any concept of the time to live for your messages?
Do we have any concept of the time to live for messages? We do for, let me see. I think the lock that we set has a time to live on it. We don't for the other types of messages because we presume something ought to read them at some point, and if it didn't, we want to know. We want to be able to find them and know about it. So we could add that. We don't at the moment because Redis doesn't have any kind of native TTL on sorted sets, I don't believe, because it's not individual keys, it's like entries in a sorted set. So we have to kind of roll our own implementation for that, whereas the locking mechanism is done with individual keys, so we can TTL that. Yeah, I think the reason we don't do it is because we would like to know, oh, there are all these stale keys that should have been processed a month ago. So what the heck is going on?
That then,